Okay, for this problem, let's try to figure out why we need to draw a free body diagram. I've already shown the free bodies here, but it's important to know that you should draw them. To do that, you first look to see if it's a dead giveaway. A dead giveaway is something that where the author asks you to calculate a force or a moment. That's a dead giveaway. The only way to do that is to have a free body diagram. That's not what's going on here, and so the next thing that you do is you count the degree of freedom. In this particular case, there happens to be 1 degree of freedom of this thing, which I'll let you figure out. If you need help with it, let me know. But anyway, it's 1 degree of freedom. What that means is if you are given one acceleration term, you can find any acceleration term that you want. So if you look at this, what is it that he's asking for? Well, for part A, he wants to know what the time it takes to pull the cord B down 7 feet. The way to do that would be to try to calculate the acceleration of point B, and knowing the acceleration of B, you can then integrate to find the position versus time. So what I need to find is I need an acceleration. I can do it without a free body as long as the author tells me one acceleration of something. In this particular case, he's not telling me that. He's just simply giving me weights and forces. So in this case, I need one acceleration term to find accelerations because it's 1 degree of freedom. He doesn't give me any of those, and so I have 0 accelerations are known, and because these are not the same, 1 and 0, I have to use a free body. That's how I know it's a free body diagram. Now, in order to do the free bodies, what you want to do is ask yourself, how many free body diagrams do you think you need? I think I need 2 of them, which I've circled here, the pulley C and the block and pulley A. So here is the free body diagram for the block A and pulley arrangement, and this one is for the C. So I'll let you sort that out. Because the ropes are different, this rope here, if you follow it around, that rope is different than this other rope here, which I'll do in blue. These ropes are different, and so they could have different tensions, and that's why here it's labeled as T. That's a T. It doesn't look good, but it's a T. That's why these tensions are different than the tensions here, because they're different ropes. Okay, so anyway, there's the free body diagrams. Once you draw the free body diagram, the next thing is to sum forces. The direction that you should sum forces is always in whatever direction makes acceleration easy. In this case, vertical and horizontal would be good directions to choose. So I'm going to sum forces and everything in the vertical direction. We're going to take this to be the positive direction. So if you do that, we'll do it for A. You have 2 T's minus mass A times G, and that equals the mass that's in the free body diagram times the acceleration of that guy. So we're going to call it acceleration of A. I'm putting it in as a positive mass times acceleration, meaning that I think that A is going to accelerate up. If I solve for the acceleration of A and I get a positive number, that means that whatever I thought it was doing, I'm right. If I get a negative, it means that whatever I thought it was doing, I was wrong. It goes the other direction. So that's the equation for that free body diagram. For the next free body diagram, you have 2T2 minus 1T. That equals the mass that's in the free body. Well, they said to ignore the masses of the pulleys. Nothing is completely massless, but what they mean is it's so light that the mass is so small that a small number times acceleration is 0. So basically this is 0. It doesn't mean that C is not accelerating. It simply means that there's no mass. Okay, so now if you circle the things that you don't know the T2. Nope, I don't know T. I don't know the acceleration of A. And right now I'm thinking maybe I don't know the tension either. So that'd be 3 unknowns and 2 equations. You've got to find another equation. Now here's a common place that students make mistakes. They panic when they get 3 unknowns and 2 equations. And rather than looking for the thing that you do in fact know, they panic and they throw something away. And one of the most common things is that students will throw away the acceleration term for some reason. Don't do that. There's something else that's known. What's known is if you look at rope number 1, they're telling you that the tension here in that rope is 10 pounds. So what they're doing is they're telling you that T2, oops, yep, I just noticed I made a mistake. I circled T 2 times, right? I want to circle this guy, T2 in the A. So they're telling you that T2 is 10 pounds, and that's given by the diagram over here. So they're pulling on it with 10. So now, how many equations do you have? You have 3 equations, 1, 2, and 3. So what you can do is you can find the acceleration of this. So it's not too hard. So if T2 is 10, you can get T out of here. So this means that T is equal to a positive 2 times 10 is 20. So the tension is 20. Right? So now you take that, put it into the top one, and 2 times T is 40. Minus mass times gravity for block A, that's 11 pounds. So mg is 11 because this is weight, not mass. You need to convert it into, anyway, so that's 11. And that equals the mass of A. Well, that's going to be 11 divided by the local gravity, 32.2, times acceleration of A. So we can find the acceleration of A. I'm going to pause while I pull out my calculator. Okay, so unless I've made a mistake on my calculator, I have calculated the acceleration of A. Notice that I get a positive number. That positive number means that whatever I thought the acceleration of A was, the direction, I'm correct. What I thought it was doing is accelerating in the positive direction, which is up. And I'm right. It does in fact go up, which is kind of obvious, I guess. Well, I guess not. I mean, it could be that B went up. If A was really heavy and you're not able to hold it up, it would accelerate downward. Okay, anyway, so it's up like I thought, and the acceleration is 84. Now, that's not what the person wants. What they want is they want the time it takes for B to move down 7 feet. So what I really would like to find is I'd like to find the acceleration of B. And then what I'll do is I'll integrate that 2 times and get the position. Okay, so is it possible to find the acceleration of B? Yes. Why? Because it's 1 degree of freedom. That means if I know one acceleration, which I do, I know the acceleration of A, it's possible to find the acceleration of any other thing in the system. So I'm going to do that. All right. Now, how do you relate one motion to another motion? You use a constraint, which we talked about in the last chapter. If you remember, the first thing that you want to do is label the distances of all of the objects that are moving. The objects that are moving are B. This point right here, we'll call that B. This point B. B is moving, and so I'm going to label a distance. Put this in a different color. I'm going to label a distance right here. We're going to call that YB. This pulley C is moving, so I'm going to label a distance down this way to Y of C. A is moving, or the pulley there is moving, so I'm going to label a distance here and call that Y of A. And then the block is also moving, but if you notice the distance between this, that's a constant. And if you remember, I'm not going to worry about constants, so I'm going to just use YA for both the mass and the pulley. YA. Okay. The next thing that you do is you write down the length of the ropes. So the length of the rope here, this little piece right here, that's equal to you take the long end and you subtract the short end. So the long end is equal to, I'm going to call it L1 for length of rope 1. It's equal to the long end is YB. The short end is a constant. Then you add a constant around the rim of this pulley. I'm not going to worry about it too much, but I'm going to add a constant in there. And then there's a distance between here and here. Piece of rope there. The long end is YC. Short end is a constant. And then there's a piece of rope right here. And that's the long end is YC minus the short end is a constant. Okay, so that's the length of rope 1. The length of rope 2, let's put that one in, and we'll put him in black. So that would be this piece here. Right, so that rope is equal to, that looks like a YA to me, minus a constant, the short end. And then there's the piece that goes from here to here, which is long end, YA, minus the short end. The short end is YC, and there's a little bit of a constant right here. There's a little constant there, so minus a little bit. Okay, so now what do you do with these rope equations after you write them? You take a derivative of them. The ropes are all constant length, and so when you take one derivative, I'm going to take two derivatives because I'm looking for acceleration. Okay, the second derivative of YB is YB double dot. If you notice there's two YC's, and so when you take a derivative of that one, you end up with 2 YC double dot. The rope 2 is also constant, so when you take its derivative, you're going to get 0. And here I have 2 YA's, so it's going to give me 2 YA double dot. And it's got 1 YC minus a YC double dot. Okay, so what is the relationship between accelerations and the Y double dots? Well, if you look at YB, if YB is getting bigger, if YB dot is positive, then YB is getting bigger. So if you have a positive YB dot, you should be having a negative velocity, right? Because the velocities are measured positive up, right? Positive is up. If YB dot is positive, it's getting bigger. That means this guy's going down. So what I know is that YB dot is opposite the acceleration of B. Okay? Well, YB is opposite the velocity, so the acceleration is also opposite the acceleration. Okay, so take a look at YC. YC is, or YA. YA dot, right here. If YA dot is positive, this guy is going down. So YA dot is negative the velocity of A, right? Because if YA dot is positive, it's getting bigger. If it's getting bigger, it's going down. So the velocity is opposite the derivative. So YA dot is equal to a negative velocity of A. So the double dot is negative acceleration of A. Okay, so let me convert these equations. So 0 equals, let me put it in a different color so it'll be less confusing, I think. 0 equals YB double dot, that's a negative AB, plus 2 YC double dot. 2 YC double dot is, I don't know, so I'm just going to put it in as YC double dot. Okay, second equation, 0 equals YA double dot is a negative A, so this would be minus 2 acceleration of A minus YC double dot. Now, We circled unknowns up here. I have 3 unknowns in the top equations. And so let's circle them down here. I also have, let's see, AB. I haven't counted that one yet. So here's another one. YC double dot. Haven't counted this one. YA dot or AA. I've counted him. Okay, so total I have 1, 2, 3 up here. I have 4, 5 down there. So total I have 5 unknowns. Let's count the equations. Up here I have 3 equations, 1, 2, 3. Down here I have 2 more, so I have 5 equations. So I can then solve for everything that's circled. I've already solved for the things up there, so let's put them in down here. So AA is a positive 84.9, so this is going to be 0 equals, this equation right here, 0 equals minus 2 times 84.9. minus YC double dot. So YC double dot is equal to negative 169.8, I think. Okay. So then you're going to take that, put it in right here. You find out that the acceleration of B is equal to 2 times YC double dot. A negative 169.8. So that would be, that's about 170, so that would be about 440. It's a negative number. So the acceleration of B is negative. Is that true? Well, remember, up is positive, so the acceleration of B is negative, down. So yeah, so that guy's going to move down. Is it constant? Yes, it is. So let's use this formula. It's x position of B equals initial position of B plus initial velocity of B times time plus 1/2. Okay, so that'd be minus 1/2 440 times time squared. So what they want me to know is how long does it take to go 7? So what's the x? The x is, we'll put the origin at where it starts. So it went down 7. It started out at the origin. It's at rest when it starts. Minus 1/2 440, that'd be 220 times time squared. So what we have is t is equal to the square root of 7 divided by 220, whatever that is. And that's it.